fantastic. That was great. Apparently equally as good. All right. I want to talk a little bit about the quiz from last time. First, I apologize. I made a typo on the second problem. Actually, it was an omission more than a typo, which makes it not an identity. So I want to go through that one. Then I also want to talk about the trig substitution stuff. I was a little surprised that it went as poorly as it did on the quiz, because you all had told me how to do the problems as we were going through them in class. So I was surprised that it didn't go as well as I had anticipated. All right, so this is what was typed on your quiz. The problem is that you need an extra -1 out here for it to actually work. It causes a little bit of issues if you don't have a -1. All right, so if we're going to go through this identity, which side do you want to work with? The left side? Yeah, good. So work with that tangent squared y over secant y -1, and then a -1. In particular, probably the easiest way to do it is to recognize what to replace this tangent y with. Remember that 1 plus tangent squared, all right, as an x, or even a theta, is secant squared theta, right? That's one of our Pythagorean identities. So what can you replace tangent squared y with using that identity? Yeah, the secant squared -1, right? You see all the top factors now. That is a top factor. Good. In fact, that's the difference of two squares now on the top, right? Got secant squared y minus a 1 squared, if you will. So I can factor it as basically, yeah, I've got a squared minus b squared, so you do a plus b times a minus b. Now what goes away? Yeah, the secant y -1 goes away. And this is why I said that I had made an error. I made an omission when I typed it up. I need an extra -1 on the end to get the ones to go away. So you should have secant y at the end. So I didn't count the problems as I made the error. Realized it after the first person turned it in, but I made an error on there. So I couldn't correct it at that point because somebody had already turned it in and left. So again, I think everybody correctly identified they should work with the left-hand side. At that point, it was just a matter of getting things to factor and cancel. It was the whole reason why I put it on there was to recognize the difference of squares so that you could factor it. That was the whole point of the problem. First one seemed to be okay. Just maybe make sure that you do your appropriate changes to sines and cosines, and as you're combining things, make sure you get common denominators. All right, so I do want to talk about the trig substitution because, like I said, I was surprised that it didn't go well because you had all told me how to do the problems in class. So let's just go through the two that we have on there. Okay. So remember, again, we're trying to recognize forms looking at these things. I either have a form that looks like constant minus variable squared, constant plus variable squared, or variable squared minus constant. Which of those three do we have? Yeah, the variable minus the constant here, right? So to start off with, we should be using which function? We should be using the secant, right? that should be our first thing. Is I know I should recognize that I need to use secant. I saw a lot of signs, right? Signs the other way. It's constant minus sine squared is what you want. The other piece that we need to do is make sure that we adjust for the constant, right? Remember, the identity is secant squared theta minus 1, right? If I just put in secant theta, do I get secant squared minus 1? No. I need to be able to factor something off so that I get a 1, right? I need to factor off this 36. So what do I need to put in front here so that when I square it, I get 36? 6, right? So when you make that substitution now, you'll get square root of 36 secant squared. And I can factor off the 36. Replace the secant squared with tangent squared, and then take your square root. So again, the first step is making sure you identify which of the three, I'll say conversions, which of the three different forms of the Pythagorean identities you need to use to start with, right? And again, it's pattern recognition. A lot of math is pattern recognition. Seeing something and then, oh, hey, I need to apply this particular technique to do it. So I see variable squared minus constant. I see variable squared minus constant. So I need to use secant. The second piece is making sure I can factor out the appropriate constant. Okay. So let's look at the other problem that was on there, which had square root of 4x squared plus 9. Which of the three forms do you see? Yeah, the tangent plus 1, right? I see variable squared plus a constant, or I could rewrite it in the other order, right? I see a sum. If I see a sum, it's got to be tangent. It's the only one that involves a sum. So I'm certainly going to start with tangent. That's the first half of the battle. The second half of the battle is figuring out what constant I need to work, correct? To be able to use the identity, I need 1 plus tangent squared. Right now, this constant is not a 1. It's a 9. I got to factor off the 9 somehow, right, when I'm done? So I got to play with this constant now. I need to get rid of this 4 and make it a 9. How do you get rid of the 4 and make it a 9? What would you need to multiply that by in order to get rid of the 4 and make it a 9? What would you need to multiply it by? 9 over 4? And then I have to do that after I've squared something. So what do you square to give you 9 over 4? Yeah, 3 halves. Good. So I need a 3 halves out in front. So you'll get square root of 4 times 9/4 tangent squared theta plus 9. Again, the whole reason why we have to do the constant adjustment is because I need to factor off the constant that's at the end there. So after we make the substitution, the 4's go a lot way like we wanted, and the 9's match so that we can factor. The tangent squared theta plus 1 is secant squared theta. We recognize that. And then we take the square root, and we get 3 secant theta when we're done. Pardon me. Again, this particular skill pops up if you need to rewrite a complicated radical expression into something that's simpler and not a radical. It pops up in Calc 2, for instance. But again, isn't 3 secant theta a lot easier to work with than the square root of 4x squared plus 9 to start with? You need to do something with it. Now, the whole process is being able to undo the whole thing as well, which we can talk about later. But this is just the idea of being able to find a substitution that you can make so that you can get rid of the radical. The problem with getting rid of the radical the way it's written is because there's a plus sign or a minus sign in the middle, and radicals don't behave nicely with respect to sums and differences. We can't break it up. Okay. But we can use trig identities to take a sum and a difference and make it a single term if we've got squares. All right. Questions on either of those two problems? Expect to see it on the next test since it didn't go well in the quiz. So make sure you review it. If you've got questions about it, I can give you a whole bunch more practice with them without any issues. I can make them up all day. All right. Like I said, if it's not making sense, come see me. I'm happy to go over it anytime. All right. So let's go back to the topic at hand that we were talking about before break, and that was looking at our sum and difference formulas for sine, cosine, and tangent, and being able to do some problems with them. In particular, we talked about doing problems of finding exact values of sine, cosine, or tangent for angles that we didn't know, but could rewrite them as sums or differences of angles that we did know. We did a bunch of those examples last time. So let's go back to problems that look a lot like what we talked about in the beginning of the semester, where you're given some information about a trig function of alpha, a trig function of beta, some other information about where the terminal side of that angle might be, and then asked to figure out some other trig functions of those angles. Before we do that, let's remind ourselves again of our formulas for sum and differences. Let me write them up here. If you have sine of alpha plus beta, how can you rewrite that?
Sine alpha cosine beta.
Yep.
Plus sine beta cosine alpha.
Good. So remember that sine, when you distribute it, or not distribute it, when you have the sum formula for sine, it mixes the sine and cosine, but keeps the same sign in the middle. SIGN in the middle. Okay. So if this were alpha minus beta, instead, you'd have a minus sign in the middle, right? What happens with cosine?
Cosine alpha cosine beta. And minus.
Good. So remember, for cosine, it goes cosine, cosine, sine, sine, but the SIGN in the middle flips, right? So for a minus here, it would be plus there. And then tangent. Was what?
Tangent alpha plus tangent beta. Over 1 minus tangent alpha tangent beta.
Good. So sum on top, product on bottom. The sign in the middle is the same on top, it flips on bottom, right? So if it were tangent of alpha minus beta, then the top would become a minus and the bottom would become a plus. So those were our three sum and difference formulas: sine, cosine, tangent. So in this particular problem, we're going to use some form of them to answer the question. All right. So let's ignore the fact right now that we're looking at sine of alpha plus beta or cosine of alpha minus beta or what have you. And just remember back to what we did when we had problems like this back at the beginning of the semester. We've got tangent of alpha equals some number, and there's some other information about sine. So remember we drew triangles and then used this information, right? So notice that tangent is negative and sine is positive. Using that information, where might you want to draw your reference triangle? What quadrant do you want to draw your reference triangle in? If your tangent is positive, tangent is negative and sine is positive. Quadrant 2, right? We'll put it in quadrant 2. Okay. So drawing that off to the side over here, I'll put my reference triangle over here in quadrant 2 for alpha. We're given tangent of alpha is negative 15 over 8. What sides can you label? Okay, you need to do the opposite and the adjacent ones. What will the opposite be? Okay, and the adjacent will be negative 8. Good. So notice that the negative is going to have to go with one or the other, right? One or the other is going to have to be negative. In this case, since we're in quadrant 2, we're to the left of the y-axis, so we'll make the adjacent side negative. Remember doing these problems like these? It's been a while. I know you've all slept since then, or at least I hope you have. Okay. Right? Can we figure out the hypotenuse from that then? Yeah, we can use Pythagorean theorem. It'll be 17. I didn't go through the work on that. I'm fairly confident you can do Pythagorean theorem. At least I hope so. All right, so I've drawn one reference triangle for the angle alpha. Let's draw another one for the angle beta. Again, with the pieces of information that you're given about beta, what quadrants should you be drawing beta in, or the terminal side of beta, as I should say? What quadrant should you draw your reference triangle in? 4. Because?
Cosine is positive in the fourth, while tangent is negative in the fourth.
Good, exactly. Secant is positive, so cosine will be positive, so you're in either 1 or 4. And it says cotangent or tangent is negative, it has to be 4 and not 1. Right? Good. So we'll draw our reference triangle down here in quadrant 4. What sides can you label? Okay, and hypotenuse will be 41, and the adjacent will be 9. We can do our opposite side. Our opposite, will it be positive or negative?
Negative.
Because it's dropping down. Good. It'll end up being negative 40 if you use your Pythagorean theorem. I picked numbers that were nice. That's why I'm not going through them. So far, so good? Pardon me. Goodness. All right, so this one wants sine of alpha plus beta. So using our sum formula for sine, we can rewrite this as sine of alpha cosine of beta plus sine of beta cosine of alpha. You told me a minute ago that was sine of alpha plus beta, right? And now we're just reading numbers off the reference triangles, just like we did at the beginning of the semester, right? Given the reference reference triangles, what is sine of alpha? So which way is it?
17.
There you go. Yeah, it's opposite over hypotenuse, right? So I'll get 15 over 17. Well, again, using the reference triangle, you want, or actually given what the given information, what is cosine of beta? Good. Sine of beta is good. And cosine of alpha is good. That okay? Do you think I expect you to do the arithmetic? Nope, sure don't. Well, what is interesting, well, at least I find it interesting. You may not find it interesting, but I find it interesting. If you were to do sine of alpha plus beta and get your common denominators, make a single fraction, and then do the same thing for cosine of alpha plus beta, you'll find another Pythagorean triple, another nice integer form of a right triangle that has integers for all three sides. Like we referred to 8, 15, 17 as a Pythagorean triple. 9, 40, 41 is a Pythagorean triple. You'll get, if you simplify this for sine, and then do another one for cosine to give you, or actually, you can just figure out the third side of the triangle if you wanted to. It'll give you another Pythagorean triple. That'll be nice. So let me show you what I mean here. If we actually simplify this, get my calculator out since I didn't bring one with me. If you do 41 times 17 is 697. And then, let's see, 15 times 9 plus 40 times 8 gives you 455. Pardon me. All right, so if you were to figure out the other side of the right triangle, so remember that sine is opposite over hypotenuse, right? So I could use the Pythagorean theorem to figure out the adjacent side. So if I do 455 squared and then subtract off the 697 squared and then take the square root, you get 528. So you end up with a right triangle where you'd have 455 on this side, 528 on this side, and 697. Like I said, this is another Pythagorean triple when you have integer values for all three sides. So if you start with two Pythagorean triples like this, you can create other ones by doing these kind of problems. Like I said, I personally find it interesting. This is a nice mathematical curiosity. I'm guessing you probably don't care, and I probably just wasted 3 minutes, but that's okay. As I always tell students, I'm in math class. I'm allowed to go off on a tangent. Ha ha ha. So I say that a lot. So anyway. Again, I don't care if you do the arithmetic simplification. If you can do up to this point here where we've got this particular sum, I'm happy. So you tell me then how we do the next problem. Good. So that's cosine alpha, cosine beta, plus sine alpha, sine beta. So yeah, the first step was to use our difference formula for cosine, right? What's next?
Cosine of alpha is negative 8 over 17. Cosine 15 over 17. And negative 40 over 41.
We already had all those values from the previous step, right? They're just in a different order. Again, don't care if you simplify that or not. Okay. All right, and then the last part. Then what would we write? Yeah, what would we write down first? Mm-hmm. Good. Again, first step is just to write out what the sum formula is for tangent. And then next step will be to replace all the numbers, right? Tangent of alpha is what in this case?
Negative 15 over 8.
Yeah, that was one that was given to us, right? Tangent of beta is?
Negative 40 over 9.
Okay. And then those will be the same values that we have, just on bottom, and they're multiplied. Do I care if you simplify that? Nope, sure don't. That's what calculators are for. My working assumption is that I assume at some point in your life you've been tested over arithmetic. When it gets down to arithmetic, I'm assuming that you can successfully type in your calculator. And I don't want you to waste time on simplifying the arithmetic. Not what the point of the problem is. Questions on that one at all? Like I said, these look exactly like problems you've done before because they're exactly like problems you've done before. We're just using a new formula to help break it up first and then applying what we've done before. So it should look very familiar. All right. Do we need to do another one, or are we okay with that one? I mean, we can do the next one if you want, but if you're good, we can go on to the other stuff. We good with this? Okay. All right. So let's go over a couple more with being able to prove some identities. Using our principles of what we've talked about, proving identities, and following that 11th commandment of using the major theorem of the section to do all problems following that section. Which of the two sides do you think you might want to work with first? The left, right? Not only does it look more complicated, we just learned about sum and difference formulas for things, right? So working with the left-hand side, we'll start with sine of x plus y minus sine of x minus y. How can we rewrite sine of x plus y? Good. We can do the exact same thing for sine of x minus y. What's the only thing that changes? The sign in the middle. Good. Now notice in this case I did put in parentheses. I need to make sure that I do the minus sign applies to the whole thing that we're using the identity for, right? Notice if you forget your minus sign, you'll get 0 when you simplify. Or sorry, not forget your minus sign. If you forget your parentheses, you'll get 0 for everything, right? But instead, we'll get sine x cosine y plus sine y cosine x, and then I'll distribute the minus sign. And now what cancels? Good. The sine x, cosine y, the first one and the third one go away. The second and the fourth are the same, aren't they? So when you add them together, how many do you have? 2 of them. And that's just in the opposite order of how the right-hand side is written. That okay? Questions on that one? We'll work on the next one for a minute, and then we will chat about it. Which side of the equation do you want to work on, left or right? I use the right just because there's more things you can do, right? In particular, I got the sine of x minus y in the numerator. I know something I can substitute for that. Agreed? Not that you couldn't do the other way. You could work with the left and get to the right. I just personally think it's a lot easier to see what's going on if we break things apart. All right, what can we replace sine of x minus y with?
Sine of x cosine y. And it's sine y cosine x.
Yeah. Okay. Well, notice that we're trying to get to the left-hand side. The left-hand side is the difference of 2 things, right? How can we rewrite what we have as the difference of 2 things?
You split the fraction.
Yeah, we just split it into 2 fractions, right? We can split it right there at the minus sign. We can rewrite this as sine x cosine y over cosine x cosine y, and then minus sine y cosine x over cosine x cosine y. It's the result of getting common denominators, right? Basically, we're just breaking it back apart again. What happens in your first term?
Sine y cancel.
And in the second one?
X is canceled.
Yeah. And so we're left with sine x over cosine x in the first one, which is tangent x. And in the second one, we have sine y over cosine y, which is tangent y. That okay? Not too bad? Pardon me. Notice in this case, it might have been, I don't know, maybe it would be just as easy to go the other way. You could rewrite tangent as sine over cosine, get sine x over cosine x minus sine y over cosine y, get a common denominator and combine them, and then recognize that you really did have the difference formula for sine. You could work backward in this case. Personally, I think it was easier to go this way than trying to go backwards, but either way works. That's okay? I'll leave the last one here for you for practice. Same kind of stuff. Okay. I think in this case, you will want to see how some things factor. You look at that one. So I'll leave that one for you for practice. Let's go on to some of these other ones where we're simplifying some different expressions. And these expressions involve inverse trig functions. So this first one says we've got sine of the inverse sine of x plus inverse tangent of y. So remember when we had expressions like this, sometimes we wrote it as, say, I think we typically used theta, but we use an alpha and a beta in this case. We said that, remember, when your inverse functions are undoing the original function, right? So rather than plugging in an angle and getting out a value, you plug in a value and get out an angle, right? But what's an equivalent way to rewrite that equation without an inverse function? How can I rewrite that equation without an inverse function in it? Take the sine of both sides, right? And rewrite it as sine of alpha equals x, right? Agree? Okay. Do the same thing over here for your inverse tangent of y. I can rewrite that as tangent of beta equals y, right? And we'll come back to this in a second, but those are equivalent expressions, yes? If I go back over here and do the substitution that I just wrote, I basically have sine of alpha plus beta, right? Using the substitutions I just made, right? I called inverse sine of x alpha. I called inverse tangent of y beta. Just plugging those in. And now I can rewrite this using our sum formula for sine. You would get sine alpha cosine beta plus sine beta cosine alpha. But I didn't start with alphas and betas. I started with x's and y's, right? And generally speaking, if I start with x's and y's, I probably want to end with x's and y's, right? But let's think about how we can simplify these expressions. Again, this is stuff that we've already done. We used triangles to help us do this. So going back over to our stuff that we did over on the side here, I can think of that as sine of alpha as x over 1. If I use a right triangle where alpha is one of the angles, what sides can you label? Opposite is x and hypotenuse is 1. Remember doing ones like these? And again, it's been a while. We can figure out an expression for the adjacent side in terms of x by using Pythagorean theorem again. You'll get square root of 1 minus x squared here. Do the same thing for beta. What sides can you label for beta? Opposite will be, okay, and the adjacent will be 1. Good. I can think of that as y over 1, so we have an opposite over adjacent. Again, Pythagorean theorem comes in handy. Didn't figure out the word I wanted to say. Comes in handy for figuring out the hypotenuse again. Remember doing ones like these? I mean, like I said, it's been a while. It's the same concept. Actually, it's the same concept what we just did earlier today. Just have letters instead of numbers. Okay. Now look at what the problem, the original problem is asking us to find. It's asking us to find sine of alpha, sine of beta, cosine alpha, and cosine beta. Can we do that from the triangles? What is sine of alpha?
X over 1.
X over 1. Cosine of beta is
1 over root 1 plus y squared.
good. Sine of beta is good. Y over, or it's 1 over, it's y over, not 1, but it's y over, yeah, square root of 1 plus y squared, right? It's opposite over hypotenuse. Cosine of alpha is
Root 1 minus x squared over 1.
good. And generally speaking, like with the arithmetic, I don't really care if you simplify this, but since it already has a common denominator, it's not too hard to simplify. You'd have x plus y root 1 minus x squared all over root 1 plus y squared. That one's not so bad to simplify. Work on the next one for a minute, and then we'll chat about it. Only because we only have about 3 minutes left, I figure we'll go ahead and chat. All right. So, did you first do alpha is equal to inverse tangent and beta is equal to inverse sine? Rewrite your equations and get triangles set up? Are we okay with how we got those? That part okay? So, going back over to the original problem then, we would have cosine of alpha minus beta in this case, right? How would we rewrite that?
Sine of alpha times sine of beta plus cosine of alpha minus cosine of beta.
Yeah, usually we write it the other way around, but since it's plus, it won't matter. It gets right. Yep, it's cosine, cosine, sine, sine, and the sign in the middle will be a plus in this case. Yep. What is cosine of alpha?
1 over root 1 plus x squared.
Okay. And cosine of beta is?
Root 1 minus y squared over 1.
Okay. Sine of alpha is?
X over root 1 plus x squared.
Good. And sine of beta is?
Y.
Just y. Good. Again, you can leave it like this as far as I am concerned for a final answer, but since we've already got pretty much a common denominator, it's not too hard to put them together, right? We already have a ready-made common denominator there. It's not too hard to put them together. I don't really care that you do it, but you can do it pretty quickly. That's okay? I think there's one more on there so you can use for practice, right? Okay. So we've got one more thing to talk about in this particular section about using sum and difference formulas to help you rewrite functions that involve sine and cosine as a single function. So we'll talk about that next time, as well as get into some new types of identities involving sine and cosine. So we'll chat about that on Wednesday. Have a good one. We'll see you then.